The free radical reactions are unique and because they have their own special electronic structure, and but they share quite a bit of commonality with the carbocations. And so the selectivity, regioselectivity, what location the reaction choose to happen, and how we use regioselectivity in the reactions. And then we'll go over some basic mechanisms about simple alkane reaction, free radical reactions. The free radicals are the bond breaks homolytically, which means typically two atoms share one pair of electrons. These two pair of electrons, they break apart. One electron goes to the one of the atom, the other electron go to the other atom. So after forming this, the atom will have an unpaired electron. Keep in mind, this is no longer octet because it starts from octet and losing one electron. And these are the three atoms. But if the atom have groups attached, we do not call it atoms, we call it radicals. A single atom, for example, single chlorine atom or single oxygen atom, they are all radicals. But again, we do not call them radicals because they are just single atom, no groups attached. And the arrow is different also because the normal double barbed, the two backward hook, those are for pair of electrons. Now you have only one electrons in this movement, so we use only one barb, the single barb. Single barb basically represents the single electron movement. And so that's quite a difference from the double arrow we get used to. The bound dissociation energy has a lot to do with the formation of free radicals. So as you can see, the single bond need to be broken to form radicals. Then the easier or the lower bound dissociation energy, the easier to form the free radicals. And so these are I graphed based on the coloring is based on the bound energy. High bound energy tend to be more green, and the low bound energy tend to be more red, orange. So you can see those more reddish colored bonds are the low bound energy. These are the bonds most easily bound homolytically to form free radicals, such as carbon iodide bond. As we know, the iodide is a very big atom, so the bound energy is very low, very easy to form free radicals. And same with the carbon bromine bond, where the other bond, carbon fluorine bond, is very high bound energy. It's unlikely to form the free radicals. And so there's some very interesting bond that we oftentimes use in the organic chemistry to form the free radicals. One is nitrogen bromine bond, because this is very low bound energy. So oftentimes we use this bond to form radicals. And also here's the oxygen-oxygen bond. As you remember, in the alkene addition, the anti-Markovnikov reactions is catalyzed by the peroxide, ROOR. And that is because the peroxide bond, oxygen-oxygen single bond, is a fairly low bound energy, very easy to break to form the free radicals. This is the most common, even though there's some other bonds have low energy, but those compounds typically very unstable. Peroxide bond is fairly stable, but is very dissociable, become the free radicals. And among the halogens, they are oftentimes used for the free radicals. You can see the fluorine-fluorine bond, very low bound energy. This explains why the fluorine gas is so much reactive. It is so reactive that is that we cannot really use it, control it, to use it for synthesis. Most often in the organic chemistry, we use a bromine, the low bound energy, to form the free radicals and free reaction. So the more red bonds are low bound energy, they are easily form the free radicals. The structure is geometry for radicals. if you compare the carbocation, carbonyl, and free radicals, they are very different. Carbocations, because there's no electron occupy the p orbital, 3 electron groups that make a trigonal planar. The carbonyl have 1 lone pair and 3 single bond, 4 electron groups. It is actually trigonal pyramidal. So this carbonyl is not a trigonal planar, trigonal pyramidal. The common free radical on the p orbital, there's only 1 electron. So it is between the carbocation and the carbonyl. And therefore, the geometry is also in between. The geometry is slightly trigonal pyramidal, but essentially planar. And especially when this bond is fairly easy to flip inverse. This is the, it is SP, between sp2 and sp3 hybridization. And so the geometry is also in between. And also the electrons can quickly move back and forth. And so it's very rapidly inversed. Essentially, carbocations, we treat as by average a trigonal planar structure. Because by average, between these 2 trigonal pyramidal, the average is trigonal planar. And the carbocation, the free radical stability also resemble the carbocation stability, because in the p orbital now there's only 1 single electron. It is electron deficient. So therefore, similarly, just like carbocation, hyperconjugation is the main factor to affect the stability, which is those methyl groups. Okay, those methyl groups with a carbon hydrogen bond, they can partially donate their electron density to stabilize the electron deficient carbon. So basically, we see similar trend in the stability. Tertiary carbon radicals most stable, and the primary, these are methyl free radicals, the least stable. So as you can see, the stability of those reaction intermediates, it lowers the activation energy and makes the reaction pathway more selective. And also the stability affects bound energy, because the more stable carbocation, it comes from the lower bound energy as well. You can see the methyl groups, the CH bond has a 430 kilojoule. As increasing number of LQ group around this bond, the more LQ group, as you can see, the bound energy decreasing. And so the bound energy is associated with the stability of the free radicals. Now the free radicals can be stabilized by the resonance. And the resonance error pushing is different. When the single electron on the carbon that is allylic, which means it has a bond linked with a double bond. Those p orbitals on the double bond, it can help distribute the single unpaired electrons. They basically form the delocalized pi bond. And the error pushing is very different. You can see that since the single electron, when that single electron form bond, it needs cooperation from the other electron. So you can see the single electron to form double bond, it needed 2 bonds to come together. This pi bond with more mobile pi electrons break apart. One of the electrons join this initial single unpaired electrons to form a double bond. The other pi electron now becomes separated and becomes the single unpaired electrons. This is the resonance. You can see the unpaired electron, it moves location from one to the other. It's very similar to the carbocation move locations. And with a bigger, more extensive pi structure, the resonance is very similar. Once you do the homework, realize the error portion in the free radical is very different. Start from the single unpaired electrons. It will form a bond, but need cooperation, need a pair with another electron. So the other electron comes from the pi bond. And so that's the first step. After this change, you notice since two single hook arrows join together, this becomes double bond. And this pair of electrons, one electron, go back to this carbon. So this carbon, now we have unpaired electrons. So that's the first step, give you the first resonance structure. You can see the change in location for the radicals. Unpaired electron now change to a different location. Okay, so this is a little exercise that shows us this pair of this single electron will keep forming because there's a pi electrons available nearby the unpaired electrons. Then the two electrons, one of them can join this unpaired, form the next double bond. So next step, remember join the resonance structures, there's no changing in the molecular structure. It only changes the bond type, but it will not change the molecular structure. No single bond broken. So anyway, since two arrows come together, now we form double bond here. And for this double bond, since the two electrons break apart, one form double bond with here. The other double bond going here. So now the free radicals in this position. So that's our third resonance structure. What else? Yes, you can still keep moving. The moving, when you draw the Zeppelin exercise, single hook, single barred. And this pi bond, again, is a mobile pi bond. Electron can easily move away, single arrow. And there are two electrons. One of them leave, no longer participate in the pi bond. So the other need to go back to itself, single barb. So the next resonance, it will be now I notice there was one bond before, the two arrows join together, now you have the double bond. And the next, this double bond break apart. And so the one electrons go back to this carbon atom. Now you can see the unpaired electrons keep changing locations. Keep drawing the next resonance, will end up have the same first structure. So if I do that, and then this form the single radical. That's not a new structure. Next step will be not new, because if you do that resonance, error pushing, it becomes this one. So that's the four resonance structures if the carbon free radical is attached to a benzene ring. And what about the hybrid? The hybrid structures, you basically draw the backbone is still the same. 6 carbons and one more carbon here. And then you look at the each bond, what happened. Do they maintain single bond, or sometimes we see double bond in between? We kind of look into all the others. So let's start from this bond. Start versus bond, we see there's 4 resonance structures, and you can see there's first one single bond, second double, third double, number 4 is also double. So this bond is between single and double. You draw the dashed line that shows you partially, you have a partial double bond between single and double bond. And then between these two carbons, again, you look at the 4 resonance structures. What happened to those structures between these two? This bond, you can see there was a double bond. Now we have a single bond, single, single. So this bond also have some double bond nature. Have a little partial extra bond in addition to the single bond. And likewise with others. The others you look for this bond. You look at 4 resonance structures. You can see this is a single bond, single, double, double. So this bond also have partial double bond. Basically, the entire structure, in the end, you do the same way. You find out each bond also has some double bond nature. So that's the resonance. And so among all these resonance structures, there's only one unpaired electrons. This one unpaired, you can just put dot here in the middle somewhere. There's no exact, very particular, specific way to put those single unpaired electrons. You can put anywhere, because those dashed line, it means the delocalization. The delocalization of the unpaired electrons. So that's a little resonance practice on the free radical. So these are, and you can see the effect how the resonance stabilization of the radicals really reduce the bond energy. So as you will remember, the tertiary carbocations are fairly stable, very stable. But you can see when the this bond broke, feel the radical linked to the carbon-carbon double bond, which is called allylic. This energy is even lower, which means the resonance is stabilized even more than the alkyl, which is the hyperconjugation. Resonance stabilizes the free radical more effective than the hyperconjugation. When you see the double bond system become bigger, become benzene ring, the bond energy is even lower. So basically stability, a benzylic carbocation is even more stable than the allylic and then the tertiary. So the resonance effect stabilizes the radical much more than the hyperconjugation. The vinylic means when we this atom has a double bond, and this atom have two single bond and one double bond, and this bond broken. When this bond broken, it form radical. Then this radical, it should look like this. There's unpaired electron here. And this unpaired electron, notice there's a pi bond at the same time between this pi orbital and the free radical single electrons. The angle is 90 degrees. So there's no pi bond in between. There's no delocalization for the single unpaired electrons. That's why the vinylic free radicals is not being stabilized. It's actually very, very unstable because the extreme degrees of high degree of unsaturation. And you can see this bond energy is even higher than the primary free radicals, much higher. Whereas the allylic, as we discussed earlier, is very stabilized by the resonance. This is about 50 kilojoule lower than this for the allylic, whereas the vinylic is 50 kilojoule higher than that. So you can see the high degree unsaturation is not good for the stabilization when the long pair is not being delocalized. The radical electron movement, as we've seen earlier, it is the movement is very unique, different from the carbocations, different from the carbon ions. Carbon ions, more discussion will be in the next semester when you take the next semester. The free radicals, unlike a carbocation, it does not go through rearrangement. So that's the possibility of reaction is very different. There are 6 different arrow pushing patterns for the single electron, the free radicals. First one is break the bond, as we can see. That's how the free radicals are formed. By break the bond evenly split the pair of electrons. It can be either heat or light, because both will give energy to the orbital. And so the bond breakage or cleavage, it is the single bond with the 2 single arrows break apart. And by doing that, the bond breaks. The second is addition to a pi bond. Addition to a pi bond because the pi electron, which has a p orbital electrons, fairly high energy. They are more reactive. And when they react, it's very similar to the resonance, but different. Forming bond is not just single arrow come in to form a bond, because you need 2 electrons to form a bond. So therefore, the pi bond is basically the pi electron. Pi electron break even, and one of them will join the with electron from the radical to form a new bond. And the other one, the other pi electron break free from the next radical. This is the addition to a pi bond. This reaction is very useful because many plastics, it goes through the, start from the alkene and build big molecules, it goes through this procedure. And the next reaction, the hydrogen abstraction. This is a kind of reminds us of the proton transfer, but it is not proton transfer. The reactions always need the 2 arrows come together to form bond. That's a big difference. The 2 arrows come together, break bond. And the product is, especially when the X is a halogen, it forms the hydrogen halide molecule. And the product is another new free radical, the LQ group, for example. It becomes a free radical. So hydrogen abstraction, very similar to the deprotonation, but notice the difference between these two. Can also be the halogen abstraction, is when the carbon free radicals, the carbon free radical form bond with a halogen, especially chlorine, bromine, the energy fairly high, means stable. They can actually take the halogens. It's very similar to the proton abstraction, very similar. The results is you break the bond. Okay, this bond will be broken. Very similar to the RH bond broken. And after bond broken, you form the LQ halides and a halogen free radical. So that's basically the these 2, halogen abstraction and hydrogen abstraction, similar, almost no difference. And the elimination, also this has a very similar elimination reaction. This reaction seemingly not very common. Okay, this seemingly very, but it's possible. The elimination is just contrary to the addition to the alkenes. This is contrary to the second type in the previous slide. Opposite. Opposite to number 2 pathways. And this reaction is not common, okay, but it does exist. The last reaction is reverse of the homolytic cleavage, bond dissociation. It is 2 free radicals form the a neutral molecule. This reaction, however, even though it's very low chance, it will be the easiest. It has a very low activation energy and it's very quick. And so that's the, because free radicals are high energy molecules, high energy entity, and the product's neutral molecule, very stable. So this reaction, it can be very common, as we can see in the future discussions. And how to remember all these 6 different types. It is actually becomes only the 3 pairs. The bond breakage form radicals versus radicals come together. That's 1 pair. And so if you, this is good practice, you show the single arrows. Break the bond. And this bond form together. Single electron come together, form the bond. And the hydrogen abstraction, hydrogen abstraction, it is actually single, form bond is always 2 arrows come together. 2 arrows come together. And, the addition to pi bond, we don't see that much in our class. We just need to be aware of the bonding is the break the pi bond. Did not break the whole entire bond. Breaks only the pi bond. And this reaction, it is similar to an addition reaction because 2 entities become 1 piece. And the reverse for elimination, even though it's not very common, in theory it does exist. And keep in mind, most reactions are reversible. So if once 2 things can add together, combine, it certainly should be able to dissociate. And so that's the reaction. Reactions. The radical reaction, almost all the reactions has the 3 steps. And those 3 steps, we need to know some very basic steps in the alkene reactions with halogen. The 3 steps start with the initiation, forming the free radicals to begin with. And the termination is the very end. Okay, termination is basically free radicals combined together, become a neutral molecule. That's the termination. Propagation is most important. It is how the free radicals reaction can sustain, can keep going without stopping. Propagation, it is before the termination. The initiation step, it comes from the low bond energy bonds. Those low bond energies are very easy to break with light or heat and break the bond from free radicals. And the termination is just the opposite. It is the free radical combined together. It's the reverse. The propagation, let's see the propagation. Propagation, there are many different ways. There is a radical is double bond. So the propagation is maintain the existence of unpaired electrons. The number of unpaired electrons remain the same between the reactant and product. And so that's what we call a propagation. It just takes new forms. And so these are the propagation reactions. Can be the addition, hydrogen abstraction, or halogen abstraction. So these are the 3 main ways to maintain the free radical in the reaction. And so these are the hydrogen abstraction from the halogen free radicals, and can be the alkyl radical react with halogen again. The later we'll find out this reaction is very, very important for the reaction to maintain, because the free radical reaction is supposedly easy to terminate, but how come the free radical reaction can keep going, sometimes explosive? It is because it can maintain the propagation reaction, keep growing. The elimination reaction is not very common in reality because the energy is higher after the reaction, the endothermic reaction. The reaction mechanism that we know fairly well is the chlorination of methane. As we learned in the alkane, alkane is one of the least useful organic chemicals in terms of human civilization. But alkane, it can go through maybe only one of the reactions for synthesis. It is a chlorination reaction. The chlorination reaction is when the methane, the alkane, react with the halogen under light, UV light, to form the methyl chloride and hydrogen chloride. So basically, one of the CH bond breaks. The carbon combined with the chlorine, and the hydrogen combined with the other chlorine, which both come from the chlorine elements. And so the bond change, this is a change in the bond. Chlorine gas, this is part of the bond in the methane or alkane. The reaction gives us the alkyl halides and a hydrogen chloride. This reaction, if you calculate it with bond energy, it is exothermic. So it's very favorable. And entropy change is almost negligible in the entropy change. It's just the exothermic reaction. The exothermic reaction, how come the bond started? It is in the beginning between the methane and the chlorine. The chlorine have a chlorine-chlorine bond. That bond energy is only 243, whereas the CH bond in methane is much higher. So the bond actually starts from the dissociation of the chlorine molecule. And that is the initiation reaction for this process, the initiation. Initiation is under light, which is UV light, electromagnetic energy, give to the bond. It dissociates the CO2 molecule, give you 2 chlorine atoms, which are radicals. And then these 2 radicals will start attack the methane molecule through the hydrogen abstraction. And the hydrogen abstraction, it formed the HCl molecule, and at the same time formed the methyl free radical. This is fairly high energy free radical. And so this can react with many other things. It can react with chlorine atom. That would be the end of the reaction. Will not be helpful. So the reason why the reaction can sustain it is because the methyl radical, it can react with the chlorine molecule, which is a reactant, by the way. It's not an intermediate, which is a reactant. And this reaction, it abstracts chlorine from the reaction. So the reaction will form this together and the chlorine radical. So basically, these 2 steps, if we combine together, will give us maintain the, you can see the chlorine atom has been the reactant, but in the following step becomes the product. So the chlorine atom seems like not being affected through the reaction. It's always self-generating. This is the reason the reaction can sustain and complete, because the chlorine atom can react with methane, the alkane, to produce new radicals and later regenerate the chlorine radical. So in a sense, the chlorine radical is almost like a catalyst, even though it is also the product. So that's the propagation reaction. And the propagation reaction, when you do the exam homework, I hope you should be familiar with the propagation reaction. It is the initially formed, the radical from the initiation step. It reacted, form a intermediate radical. But this intermediate radical later regenerate the halogen radical through the following reaction. Among the 3 steps, initiation, propagation, termination, the propagation is a little tricky. It has 2 steps.
So Professor, yes. Okay, so the 2 steps, it's all still the same reaction. It's all one. It's just 2 steps.
Actually, the whole reaction is together 3 phases, 3 stages. The reactions combine all the 3 stages together, give us all one reaction. Yes.
Okay, thank you.
Yeah, is a reaction mechanism. If you remember in the Jenkins second semester, we have two-step reaction mechanisms. Here we have actually 4 steps in this reaction. The middle propagation is most critical and it can be confusing. Take some practice to become good at this. Yeah, the termination is easy. Terminations, basically there are so many intermediates, free radicals, and any of those free radicals, they can randomly meet each other, and that's the end, because those free radicals combined together become neutral molecules, no longer helpful for the reaction. And that's what we call a termination reaction. And so as you can see, we have a chlorine atom radical, and also we have the carbon, the methyl radical. So among those 2 kind of radicals, there are 3 ways to terminate. It can be the 2 chlorine combined together, or chlorine methyl combined together, or the methyl radicals combined together. This will give us something very interesting. This gives us the ethane, which does not show up in the overall reaction. It is actually a very, very minor byproduct. Very, very minor product in the whole reaction. The reason is just because the carbon methyl radical is so much high energy but unstable. So it's a very low amount during the reaction. The chance of those radicals collide and produce ethane is extremely low. And if you talk about this reaction regenerates chlorine gas, so it doesn't affect anything. You won't see that in the results. And this termination gives us a product. By the way, we have a 2-step to give us product. And go back to the previous slide. The second step in the propagation gives us 1 product. And first step in the reaction gives us the other product, hydrogen chloride. The propagation step is mainly responsible for giving us the product, not the termination. Because termination, we're talking about a very low concentration of the high energy radicals react to each other. And this kind of a way to form product is highly unlikely. And this is simply just too low probability to give us a very, very minor product in the reaction. So these are the coupling of the radicals to give us neutral molecules. And so the reactions, if you combine the propagation steps together, will give us, there are 2 steps in the propagation. There's a hydrogen abstraction and a halogen abstraction. When these 2 combine together, as you can see, these 2 canceled. Chlorine atom canceled. So the net combined reaction, it is just what we observed, the overall reaction. So that is the propagation step. It is we call it self-sustaining, which is the typical for chain reaction. Most combustion reactions and explosion reactions are the self-sustaining reaction. It is basically in the middle steps, the product becomes reactant in the next step. And the reactant keeps feeding themselves until all the reactant consumed. So as you can see for the reaction, as the reaction goes by, we consume more chlorine and methane. Eventually the reaction will stop. So that's the radical reaction mechanism. This is the only reaction that we need to be familiar and know how to write those steps. We have some other reactions, but this is reaction is fundamentally shows us those 3 stages: initiation, propagation, and termination. And this reaction we also call a chain reaction because in the middle of those steps, those reaction intermediates becomes reactant for the next step. And the next step regenerate those reaction intermediates. And so that's why we call it it's self-sustaining. Self-sustaining. As long as there's light available, the reaction can sustain. The chain reaction, it is basically the, by definition, is there are multiple steps in those reactions. And earlier steps, the product, it produces a reactant for the following step. And the following step produces a product which is good for the initial first step of the reaction, self-feeding reaction. So that's what we call a chain reaction. This reaction, methane reacts with chlorine, unfortunately is not clean because the first step reaction product give you methyl chlorine. But this has more carbon-hydrogen bond. It can still react with chlorine radical or the carbon radical, keep more reactions. It keeps losing the hydrogen. Next step become dichloromethane or methylene chloride, which is the same thing. This compound has two names. It depends on what you look at this. This in organic chemistry, we call it methylene. It's almost like a single carbon try to form double bond. And also we can call it dichloromethane. Anyway, there's more carbon hydrogen, so can have more reactions. This will be the trichloromethane, but the street name we call it chloroform is the most common form of anesthesia. Sometimes bad guys use a towel soaked with chloroform and put on the victim's mouth, and the victim once breathes in chloroform, they completely pass out because it's good for anesthesia. Anyway, there's still one more carbon, so eventually give us a carbon tetrachloride, a perfectly nonpolar tetrahedral molecule, used mainly for the solvent. So the polar chlorination is very difficult to control. Chlorination reaction generally not very useful for synthesis because it cannot control. And chlorine is very reactive. The fast reactions oftentimes difficult to obtain to get a major product. You know, a whole bunch of product all showed up. So that's the reaction mechanism for the free radical reaction. There are many other reactions. Unfortunately, we cannot start from a single halogen and form radicals. We need something to help form the radicals. That's the radical initiators. We've seen some of them in the earlier chapters, which is the alkene anti-Markovnikov reaction, where we added the peroxide as the reaction condition. Peroxide in that reaction, it is the free radical initiator. And so, for example, we can see the chlorine-chlorine bond is one of the low bond energy. The energy is very low. Peroxide bond, it has even lower bond energy, which makes them ideal for radical initiator. And peroxide is relatively easy to make. So this is a very common initiator for radical reactions. And this bond is the acyl peroxide. It is basically, this part is very much related to the acetate ion. And you have a molecule made of similarly two acetate ions. This molecule bond energy is even lower than the peroxide, alkyl peroxide, because the carbonyl group strongly pulls electrons away from the oxygen. That makes the oxygen-oxygen bond even weaker because there's less electron density in between these two oxygens. So anyway, peroxide is even stronger initiator. Initiator basically realize peroxide and those initiators in the reaction that help you decide what kind of reaction will progress. For example, will the reaction give us a Markovnikov or anti-Markovnikov? the peroxide called the anti-Markovnikov halogenation or hydration reaction. And O2, oxygen. O2 is abundant in the air. For organic free radical reactions, unfortunately, O2 is a terminator. Okay, that's why I have a R note here. It's terminator. Because O2, based on the molecular orbital series, it has 2 unpaired electrons. And that is why the oxygen gas, O2, are paramagnetic, because it has 2 unpaired electrons. It is basically a diradical. The diradical is very abundant in the air, and since the radical and a very large amount, because in the air we breathe, 20% is O2. So if those organic free radical reactions try to progress in the air, just becomes very difficult, because oxygen, it has diradicals. It can react with those radicals and terminate the reaction. And so the free radical reaction, in reality, we need to maintain the environment is oxygen free from oxygen. So for example, we can flush with plenty of nitrogen gas. Nitrogen gas not dimadical, it's not diradical. It can remove to push away the O2 and maintain the environment conducive, helpful for the radical reactions. So that's in organic chemistry, O2 is enemy for most organic chemical reactions. One is moisture, the other is oxygen gas. Both easily ruin the organic chemical reactions. Inhibitors, these are we just need to know. We don't need to really get into too much about those. These are quinones. It's kind of diketon. They react with the radicals and become stabilized. And once become stabilized, by the way, which means it'll be less reactive. So therefore, they are just like a traps. When they see free radicals around, they will react with them and become stabilized and become sedated, basically. No longer be able to react. So that's why we use as an inhibitor. In organic chemistry, we try to stay away from inhibitor. Maybe unless in the inhibitor in health is very important, because our body, the body aging process, as we know, has a lot to do with the free radicals. And so to remove the free radical in our body it helps slow down the aging process. And red wine, for example, has many polyphenols. And this, as a matter of fact, is one of the polyphenol. And so since polyphenol, it can easily become quinone and remove free radicals. And that's why people believe the red wine and some other, and the grape seed, grape skin has plenty of polyphenol. Those are good for anti-aging process because they remove the free radicals. Halogenation regioselectivity. This is about where does the halogenation, which is alkane reaction with halogen, how does the reaction takes place? When the bigger alkane get involved in the halogenation, and there's a matter of which carbon, which degrees of carbon is more preferred in the free radical reactions. So let's say we have a propane. This is a propane molecule. Propane molecules, there are two terminal carbons. Each are basically considered as a methyl group. In the middle, there's a methylene group, which is CH2. And so there's only 2 hydrogens in the middle, and there's 6 hydrogens on the outside. And when this kind of propane react with chlorine, and if we can maintain only monohalogenated, okay, has a monohalogenated, have only single halogen react with the propane, there should be 2 products. One is the middle carbon react with the chlorine, bind with chlorine. The other is terminal carbon bind with chlorine. And if you just look at the probability, there are 6 methyl hydrogens, only 2 methylene hydrogens. So the chance of getting the terminal product, the chance should be 6 versus 2, just by random statistics. So we would expect the the chlorine attached to the terminal carbon should be in the major product. Then the middle carbon form bound with chlorine. But this is not what you find from the experiment. So the fascinating reaction is, this is the experiment results. The methylene, even though it has only 2 hydrogens, it is actually the major product compared with terminal methyl hydrogen reacted with chlorine. So the pattern is secondary carbon hydrogen is just more preferred over the primary. This can be easily explained by the stability of the free radicals. The secondary carbon radical is more stable than the primary radical. So this is the main reason we have the middle carbon form bound with the chlorine. Because the secondary radical is much more stable, it lowers the reaction activation energy and make the reaction more competitive, even though the chance of the probabilities is lower. The reaction rate faster with the secondary radicals that compensate for the lesser probability due to the lower amount of hydrogen available. So that's basically the, and for this reaction, we find out the reactions is both thermodynamically, which means lower free energy, and also the secondary radical reactions have a lower activation energy as well. Therefore, it is faster. So the both thermodynamic and kinetic favored cannot be beaten. This is it's always preferred. What situation was preferred? It doesn't matter how low temperature or high temperature. The secondary product always major product. This preference for the secondary or tertiary is even more pronounced when we use the bromine reaction, the bromination reaction. It is basically the bromine element react with the alkane to form alkyl bromide and the other product, which is hydrogen bromide. This reaction, you can see the even stronger preference on the secondary carbon. The ratio, it is basically 32 to 1 ratio. And basically you could exclusively, almost exclusively, the secondary carbon form bromide. Now this reaction become much more useful, because next step, we can use elimination reaction to give us alkene. And with the alkene, in the future chapters, we can learn it can form a whole host of all different compounds. And so in the next chapter, in the radical chapter, in the future chapters, many reactions, if we start from the alkane, we use bromination. The bromination reaction produce exclusively only one alkyl bromide based on the carbon radical stability. And once you get a single product, you can use elimination to form alkene, and then you can find all these other products. So the difference between the chlorination and bromination, you can see the chlorination reaction, the ratio is about 2 to 1. And when you have the, oh, by the way, this is different reactant. We get this has a capability to form the tertiary carbon radical. And the tertiary carbon radical, as you remember, the tertiary carbon radical is even more stable than the secondary. And as a matter of fact, we see the very significant. In the chlorination reaction, the ratio between the tertiary carbon halides versus the terminal is about 2-to-1 ratio. By the way, this is phenomenal because there's only one tertiary hydrogen here, and there are 12 terminal hydrogens. Just by the statistics, the chance of forming this halide, monohalide, it should be 12 times higher than the tertiary carbon from halides. That's based on the number of hydrogen atoms available. But the reality is still, this free radical is so much more stable. It still becomes a major product. So the ratio becomes 2-to-1 ratio. This is phenomenal. It just completely beat the odds of, even though the number of hydrogens on the terminal is just so abundant, but still got only a very minor product. Okay, with the bromination, this is just amazing. Bromination, we got almost none terminally formed bromide, exclusively formed the tertiary bromide. So again, because this radical, tertiary radical, similar to the carbocation, is much more stable than the secondary carbon radical. And that's why we have such stronger preference forming this. The reason just because these are the list compares the halogenations, and for the fluorine, this we find out the ratio among the 3 different positions, the ratio between these 3. The fluorine, you can see the primary is 1, secondary is a little bit more preferred, tertiary a little bit even more, but not much. The ratio is very close to 1. That means among different different substitution product, it's very similar ratio. So for synthesis, this is not good because you get a almost evenly distributed product among all different positions. The chlorine, you can see it can be useful because there's a fairly strong preference for the secondary or tertiary. The ratio between the terminal and the other secondary or tertiary is about 5-to-1. So among those, you get 80% are the major product, 80% major product. With bromine is the best because bromine, when you have alkane, all 3 different kind of carbons can form halides. It forms exclusively the tertiary. If there's no tertiary, you should get 80%. You get 80-90% are the secondary radicals. So the bromine shows a stronger preference on the tertiary or secondary, which will make the bromine very, very useful for synthesis. Whereas the other 2, especially fluorine's reaction too fast and indiscriminative, will not differentiate, give you a whole bunch of product. It's pretty much useless. Chlorine, under very limited conditions, we can use chlorine. Bromine is a favorable way to achieve the reactions. The downside with the bromine reaction, it is the cost. Bromine is one of the rare halogens in nature. It's just more expensive, and the bromine elements are fairly very corrosive as a liquid. So today we'll just stop here.